So what I'm going to talk about is how things look from an end system. I mean, DPDK is used for routers and switches, and we know how it works with Latency switch and the hot potato forwarding case really well, where you get a packet, do a pattern match, apply some rule, and then send it out some other port. But we don't talk so much about what this looks like for an end system. So what I'm going to start talking about is what sort of networking paradigms that we have at Oracle, where we have a lot of database and cluster applications. We are interested in reducing latency, and that's the big selling point about DPDK. So I'll talk about some experiments that I've tried to use DPDK in these paradigms. This is still work in process, and I'll share some of my preliminary latency measurements with you. And more importantly, the software engineering considerations that come up when you try to fit DPDK within these networking models. And finally, the current conclusions that I have from these experiments, and hopefully leave plenty of time for discussion to see if others have had the same experiences, what could be done differently in DPDK, and what could be done differently in the application. So let's start by first looking at the Oracle problem space that we typically encounter. These are request-response transaction-based models. Our applications are multi-threaded, and each application typically has multiple descriptors. Now, the important point to note is I said descriptor, not a socket. So I/O comes from many places. Networking is just one of them. We have to deal with disk I/O, file systems, and also sockets. So the application has to dispatch between all of these. In terms of networking, our transactions are mostly done over datagram sockets. And what happens there is we use BSD-like, POSIX-like socket APIs. That means it might not be perfect POSIX, but it's going to look like that a lot. Our networking performance challenges are mostly in the datagram socket area, and we use two types of datagram sockets. One is UDP, which most people have used, and the other thing is we have an Oracle-specific protocol called RDS, which stands for Reliable Datagram Socket Service, which is also a datagram socket. So UDP is probably well known to everybody, but RDS probably not so much. So let me talk a little bit about what RDS is. RDS presents a datagram model to the application. So the application can do send message and receive message, and it sees message boundaries. But underneath, that message gets sent over a reliable service. That means something that guarantees reliable order delivery, retransmissions, and all those things. So that can be done in multiple ways. One way is to send that message over InfiniBand, in which case we bypass the TCP/IP stack, which is what we do with DPDK also. And the other way to use a reliable transport underneath is to use TCP/IP Ethernet, right? And that's where DPDK becomes interesting to us. So just the other way you could do this with UDP sockets, the model is similar. The application sees a datagram socket, but there the user space has to do extra work to keep track of state. So it has to make sure, put sequence numbers, make sure the thing got the other side, do a reliable order delivery, work out the congestion, all the other extra state. So why is DPDK interesting in this space? We have services that are CPU bound and latency sensitive. That is not necessarily because of the I/O. That is because we have to do other things which are CPU bound. So anything we can shave off from the network I/O is interesting to us. Now, DPDK allows us to read packets directly from the driver. We've already done that with InfiniBand, so we have some history there. And we also already have the infrastructure to do the reliable, guaranteed order delivery and so on. So that's from the UDP sockets. So we also have some history there, right? So we have some degrees of freedom here where we have pieces of software that you could potentially glue together with DPDK. Also with RDS, what happens is you take the application payload and encrypt it in your own header, which is the RDS payload. So we have a degree of freedom there as well. So the idea was to try to see if we could use DPDK in this model with all these other pieces and get something interesting. Right. At the same time, DPDK gives us everything from the driver, all frames. Right? And it goes to this user space spool mode driver. And we are not interested in boiling the ocean. We don't want to implement every IETF and IEEE protocol. We are only interested in processing a subset of flows. So the most obvious thing to try to use was KNI, because that's the most obvious thing documented there. So what I tried was to register a receive-side callback with KNI, which would look at a packet, do some pattern match, and say this is an interesting packet. And the other uninteresting packets, which are still useful packets. These are things like NFS, SMTP, IP fragments, good stuff, but I'm just not interested to this Oracle application simulator. Feed it back to the kernel through KNI's vEtex. So an immediate observation about this approach is that it's going to slow down the Linux TCP/IP stack. Right? So what happens to the NFS or SMTP packet is it goes up to the user space driver, it rejects it, sends it back, then it goes up the Linux stack and then gets processed the normal Linux way. Right? So I wanted to measure how much penalty that is. So I tried instrumenting 3 different types of things. One is what I call the direct path to DPDK, so where you get something through the IGBU IO up to the pole mode driver. It goes to my callback. My callback is going to do a very simple thing. It's just going to reverse DMAC and SMAC and feed it back in. I'm going to measure the RTT for that. The other is the slow path, which is go up to DPDK, go down the FIFO shared memory, go up vEth, go to the Linux application, have a PF packet application which switches the DMAC and SMAC, send that back down. And the third one is the control, which is remove DPDK from the picture, just use PF packet. What is the round trip time you get there? So other details about this experiment, they were small size packets, 64 byte size packet. What I was using to match on the flow was an experimental ether type, so it was a very simple pattern match, no deep packet inspection involved. And as I said, the application was not doing anything special. It was just reflecting the packets back. And these were the latency estimates. So the direct path to DPDK is the shortest time, which is good, 90 microseconds. PF packet is slower, but not that much slower, given the other factors involved. But the thing to note here is that all those packets, the NFS, SMTP, all that stuff is much worse. So we're talking about 2 milliseconds versus something like 100 microseconds for the other two. Right? So that's a very large penalty. And that would not be a good thing to put in production. So when you look around, the common practice that seems to be there for traffic bifurcation, I have a couple of pointers here. I'm going to focus on the first one, the one that uses SRIOV for traffic bifurcation. So basically what is described there is you create a VF over your NIC, and your DPDK sits on top of that VF. The PF is still going to feed your NFS, SSH, SMTP, all the standard packets. And your DPDK application would, in my case, process the interesting packets based on the ether type and reflect them back. So this would work great for the ingress path, right? Because now you don't have the latency that you had through KNI. However, for the egress path, as soon as you have anything that is not a trivial form of routing, as soon as you have non-trivial routing, forwarding, ARP, filtering rules, there's going to be a problem because your DPDK needs to learn those rules. There is no control plane by default in the virtual function path. Also, there are additional problems, right? If you are doing a pattern match on the packet by a 4-tuple, which is the common case, IP fragments will blow that algorithm, right? So you have to deal with IP fragmentation and reassembly. Now, in the DPDK set, there are examples that show you how to do IP fragmentation and reassembly, but I would argue that fragmentation and reassembly are the slow path. So no need to reinvent this in DPDK, just use the kernel stack implementation. It's good enough, it's fast enough, right? Let the kernel reassemble it and let that go the slow path. Fix your fragmentation problem by fixing your network topology. But if you want to do that, your application has to now be able to straddle both the DPDK path and the Linux path, because it could get something that the kernel had reassembled, or it could get something that is coming up the DPDK fast path. So it needs to be able to straddle the boundary. Also, the first thing I said was we deal with things that is more than just network sockets. We deal with disk I/O, file systems, and so on. So if you want to listen across all these descriptors, the prescribed way to do that is with select or poll or epoll, right? And the classic network paradigm that you will see is the dispatcher that I've showed over here, where your application will block and sleep on select, and it will get woken up either because an interrupt or seek poll happened, otherwise some I/O is available. The application does its own dispatcher loop using its own priority to figure out which file descriptors to handle and in what order to handle them. If the incoming I/O is because of a TCP connection request, for example, you accept it, add that file descriptor to your set, and go back to listening. Otherwise, you do your request response, right? This is the classic model that you would see. But how to map this to DPDK? I looked and I looked and I asked, and actually Heel and Jang gave me this suggestion here, which is try to use RX interrupt mechanism, have and wait on a thread per FD. The thread will be woken up when packets arrive. I never got around to trying this, and I certainly can. But one objection that I have to that is it will require a major application rewrite to adapt to this. And that's not an easy thing to do if you're dealing with a large mass of software. Right? Moreover, there's another problem with this, which is that depending on how you look at it, if you look at the DPDK as a library, you have just changed the application's threading model by adding these extra threads. So if my application thinks it's single-threaded, it can reasonably assume that SIG-inter and SIG-pol will be delivered to its thread. But by adding extra thread, you've broken that assumption. Right? So there are other problems with this. I looked at the examples, and there is a netmap compat, which gives you a file descriptor which you can sort of kind of poll. But there are lots of restrictions, so it's not really something that I could add to my mix of disk I/O and file system and other descriptors. Also, I'm still doing performance comparisons. I don't see any big win of using this netmap compat over the native netmap, so that doesn't seem like a viable option. Then there is this thing of busy poll. Right? It's a poll mode driver. That's the selling point to make it fast. Now, when I run the KNI example with this command line, which is pretty daunting, but I will not go into the details, let's focus on the last thing, the 045 part. Right? That says use CPU 4 for RX, CPU 5 for TX. Right? If you run this example and have no network traffic, you will see that CPUs 4 and 5 report 0% idle. They're 100% busy. Even though there is no traffic flowing, there's no work being done. That is not a healthy system. Right? And the 100% polling has other problems. In NetDev 0.0, Stephen Heminger pointed this out. There are CPU power limits, PCI bus overhead to deal with. So in that NetDev talk, Stephen suggests to put a sleep in there so that you don't have this CPU being 100% busy. And that works, but it's still a brittle system because you have to now figure out how long to sleep. And the more elegant way to do this is to use select or poll or epoll and just be woken up when data is ready. Right? So the current conclusions that I have from all of this is that DPDK is good for the hot potato forwarding use case where you're doing nothing but networking, where you just like Open vSwitch, where you have some OpenFlow or something else feeding you the control plane and setting up your rules, and then all you do is you look at a packet, do a pattern match, and based on your rules, modify it and send it out another port. That's good, right? But for the end system use cases, we have to deal with APIs. They matter to us because we are dealing with a very large system of software, and we need to have something that fits with the rest of the system. The ease of programmability is important to us, right? And then there's the other thing which was brought up earlier from the customer survey. We need to be able to coexist with the existing kernel stack so that we don't have to reinvent a new way to do BGP and OSPF and IP fragmentation and reassembly and all these things for the uninteresting flows, but very useful flows, right? And the other factor is also just control plane considerations. When you start using DPDK, the system suddenly becomes much harder to observe. You cannot really use ETH tool. There's an ETH tool, but it doesn't give you the same information. Configuration is done differently, so that's just, an administrator would not be able to feel good about that. So that's pretty much what I had to say, and I'm interested in any comments or any other things that we could or should have tried.
So when you said that you were getting 100% CPU usage, right?
Yeah.
I mean, would it be possible to use a C group config to limit that? To limit the number of CPU shares?
I suppose we could, but that's so the obvious way to do it with select, right? But if you use C group configs, what's that going to do the performance? I don't think that you would have the same performance anymore. So
right. I mean, I'm not familiar with the application or how many cores as such that you can dedicate to this loop that you have. But okay, then going to the select poll mode, right? So I guess you have tried something like VFIO, right? Or UIO to get basically a FD on which you can select on.
I was doing this on bare metal. I did not try any virtualization or anything. So.
Yeah, even with that, it's something like your RX interrupt, essentially,
okay.
Handling in user space via file event.
Okay.
Right. So yeah, just some observations.
All right.
Any other questions? Or, yeah, actually, John is making a good point. So not necessarily questions, but suggestions on how to resolve it. So it's you know,
I don't
an
think there's a
expansion
simple
on
answer,
yeah,
yeah.
that's the problem. That's what we need to think about.
Yeah.
Jim, maybe.
I know this is the DPDK summit, but some of there are a few advantages to programming model with things like NetMap.
We are looking at NetMap as
Right.
well. And this was the DPDK summit, so I didn't go there.
But there is this whole sort of, what do we do about KNI? And there's an interesting model in NetMap that largely,
And that
gets
was
rid of some of the overhead.
But that's a good point. That was actually the reason why I looked at NMAP Compat to see if you can use that. But NetMap is more fits better with
It's
the
never
others.
going to be as fast as DPDK, but there are some. It's much easier to program against.
What I would say, and I was suggesting this to Venki as well, is the NetMap model tells you that if you have a proper file descriptor, it's much easier it's easier to contain the scope. And if we can build DPDK under PF packet, that might be interesting. Steve.
There is an example that's the I think it's under L3 forward power that uses the interrupt descriptor method.
I will take a look. No, I didn't
the
remember.
problem with that is that only some drivers support it.
I see.
It bounces between interrupt mode and poll mode.
Yeah, it bounces between interrupt and poll mode. It's a good example, and I would recommend people look at it.
I'll do that.
Okay, and so the conclusion is Oracle keen to use DPDK in the future?
Is Oracle what?
Oracle keen to use DPDK in the
We're
future?
keen to reduce our latency, by whatever method that works for us.
Okay, so no in the near future.
No, we are not religious about any particular.
Okay, and do you plan to use this kind of solution in virtualized environment? In virtualization?
Eventually, but
Yeah.
first we have to get the bare metal thing going first.
Okay, thank you.
So why not use message passing interface or anything? OpenMPI, low latency stuff.
I have not looked at OpenMPI. I will look at it, but there's too many different ways to do this. So.
Thanks. You mentioned that you're keen to reduce the latency. Do you have a sense for what the NIC to application latency component is as an overhead of the database's request processing time? Like, what are the stakes?
I have not instrumented that particular one yet, and these are, as I said, this is still work in progress, so we're trying to get some real-world examples from the database group, and certainly if I have those numbers, I will share them on the list.
But do you, I mean, just in ballpark terms, is this a dominant cost of the application request processing?
That is what we believe, but we have not instrumented the exact numbers yet.
Okay.
So the database has some overhead as well, which is very CPU intensive because it's a graph theory problem. So
I have a question.
So once you see the packet, right? Like, do you run your own TCP/IP stack on top of the buffer?
I was trying to avoid that because if I add the TCP/IP stack, then the question becomes: is it slow because of the TCP/IP stack or because of something else? So that is why my callback is very simple. It just reflects the packet and does not do any special processing.
Okay.
Thank you.
So, quick question. So you have put some latency measurements.
Yes.
What about throughput measurement?
I was focusing on latency because, so we tried this with NetMap, and this is the DPDK summit. But with NetMap, we can get line speed, right? And we still we're able to coexist with the TCP/IP stack and everything. I don't have the throughput measurements for DPDK. Because for us, we are more interested in the latency because it's a request response, so the sender is blocked until the receiver does the response. So we start with latency first. So.
And why not putting your application in the Linux kernel? So if latency is so important and you want the flexibility of the kernel.
Yes.
Why don't you put your application in the kernel?
Because we have all this database stuff that actually needs to be done, and then you're starting to bloat the kernel at that point, and at some point it gets impractical. It has to go up to user space where something has to process it. And so on.
Any other questions?
What do you want the community to do? How can they help you?
Like I said, it would be nice if we could have something like PF packet, and you could tell us this is a faster PF packet because we have some DPDK shim under it. Right? Then my software engineering consideration becomes just use PF packet. You may or may not have the acceleration from DPDK. So that would be attractive to us because then we don't have to change our entire programming model. Or give us something like netmap, which is a file descriptor, and then I can listen on PF Netlink and build my control plane. I'm willing to do that. But at this point, it becomes an either-or proposition. DPDK takes over the entire NIC, and then I have to figure out the control plane on how to send this packet out, listen for ARP, figure out if something changed. That becomes much more difficult if I don't have a descriptor that I can select on. And, excuse me? I want to see if this is interesting to me, right? I want to be able to cherry pick things out of DPDK that give me acceleration and not have to take the whole thing or else.
So DPDK rings are kind of similar to AF packet in a way, except for, of course, you have to spin a core to consume the packets.
Correct.
So that's the approach I took some years ago when I was trying to get an application accelerated by DPDK. I just used the DPDK ring and then expanded that and consumed the packets in a thread that was running on DPDK ring. But that doesn't give you a socket interface. It doesn't give you interruptibility and so on.
Right. We contribute back. I have contributed to the Linux kernel, so we contribute as we find something useful to do. So.
Okay.
Thank you.
Thanks so many.